Hello. How's it going?
Am I the only one here?
You're the only one here so far.
Wow. Wow. You really lighting up a storm lately.
Yeah, thanks. Well, thanks for coming.
Thanks. I'm just learning a little bit of information. It's as much as I could do, learn a little bit.
Oh, sure. Yeah, hopefully people will come today because the thing that I was going to talk about, I have to say, is one of my favorite little mathematical constructions.
Hmm.
Oh, we got one more person. Got a Michael coming in.
Oh, Michael. Oh, he's committed.
Oh, yeah. You can say that again. Hello.
Hey, Michael.
Matthew Weiss. You know, I tried to access the Barry Robbins paper,
Yeah?
but of course you have to be a member of all kinds of different organizations.
Oh, I thought I put
How did you access it? Did you read the original paper?
yeah. Oh, see, look, I put a link. Yeah, I broke the copyright law.
Could
And
you put the link back so we could access it?
yeah. Here, I'll show you where to get
Because
it.
you have to be a member of an organization which I wouldn't join.
Yeah, I've been taking these classes,
Yeah.
and one of the nice things is getting that like academic
Yeah,
library.
well, if you're a student, you can get it, yeah. But as Groucho Marx once said, I wouldn't become a member of any organization that would have me as a member.
For sure.
But I'm bummed.
Yeah, if you go to here, I put it under the,
Oh, okay.
and then if you go down at the bottom.
How do I access this?
Oh,
Which,
um,
it's one of the previous, could you put this on the current website? Because this is on one of the previous websites, isn't it?
well, I've been updating this page the whole time, basically, just popping.
But I mean, the link is not on the. How do I find the link to this?
It's on the one from last week, basically.
Oh, really? The last week's link? Oh, okay, that's good.
Yeah,
So Matthew, the other Matthew from New Jersey, you're both from New Jersey, right? So how come we don't see you at the New York meetup?
I've had little time. I need to concentrate on something that I can show as feasible.
Really?
Yeah.
Doesn't quantum physics tell us that nothing is feasible?
Well, yeah. How's it been going there? I heard Barry's doing a little quantum gravity.
Yeah, he's in transit now, so we're not going to have one this week. So, yeah, it's what Barry is interested in. I think it's a little incomplete, but I've been reading some background material on my own, but I'm still not entirely clear why QED is renormalizable and gravity is not. It has to do with the fact that the gravitational constant is dimensionful, but you can make it dimensionless. You can make it dimensionless for a specific particle, like an electron, which is what they do in QED. But are you following me? I mean, have you looked into this?
I'm not like all that familiar with the technical arguments, I have to say, but I mean, like my like dumb intuition about it is just like, well, since gravity itself can gravitate, maybe you get a kind of crazy
Well, that has to do with the metric.
runaway effect.
You're not in a fixed metric background. That's one of the problems with gravity. But the approach that Barry's taking, comparing it, let's say, to QED, which is renormalizable because the fine structure constant is less than 1, so it converges. But you could do that artificially with the gravitational constant, but for some reason, you can't.
Yeah. I mean, I've seen people, you know.
You can make it dimensionless, the same way they make the fine structure constant dimensionless. But for some reason, it doesn't work. And I'm not entirely clear. I think it would work on the atomic scale, but not on the Planck scale. The problem is that when you get down to the Planck scale, where quantum gravity supposedly kicks in, it does not converge. So I don't know. I'm not entirely sure that gravity is a quantum theory.
Yeah,
There's no empirical evidence, and I'm the big empirical evidence guy.
I saw this paper the other day. It was like great. It reminded me of back in the '90s, that famous paper "World is Hologram," which everyone was loved. And I saw this today. World is neural network. Which
yeah, well, but the thing is, it's still, these are still theories. They're not, until there's empirical evidence. In my view, it's not physics. Now with QED, we know that's physics because there's empirical evidence for it. But in the case of quantum gravity, we talk about gravitons. Show me one. Nobody's ever discovered it.
Yeah.
And they talk about it as if, well, it's a done deal. So, but of course, that's a difference in philosophy between a physics theorist and a physics practitioner. And I, being an engineer, I need to see the empirical evidence, or else it's just a theory.
Yeah. That's fair. Yeah, I thought this paper was pretty funny. I didn't really read it that closely, but.
Well, I mean, this is like the what would we call this?
Well, I mean, you'd appreciate it because they sort of like
this is where space is emergent.
Yeah,
right?
yeah. They sort of have differential equations to describe the dynamics of neural networks, then like look at like different like limits of it. And in one, they're like, oh, look, it looks kind of like general relativity. And then like in some other limit, they're like, oh, they're sort of like when the neural networks are like super sparse, basically, they're like, general relativity could like approximate some of its dynamics. And then they're like, when the network's really shallow and interconnected, then quantum mechanics describes it better.
Well, this is like spin networks. Spin networks lead to the emergence.
Well,
space-time.
It's a particular, I guess, they do it in the context of like neural networks, which are like, already in the same mathematical universe, I've always thought, as, quantum mechanics. In other words, like what is a neural network but a matrix?
So you're telling me
neurons, but then the difference is that there's like this activation function. You know what I'm saying? Like you'll have a neuron, it's like, and then there's like a bunch of neurons connected to it, right? And then like each one has a weight, and you multiply the activations of the incoming neurons by all the weights, and you get the activation of a particular neuron. But then there's always a nonlinear function that they use to like squish the output in a neural network, whether that's like they're gonna cap it at a threshold and be like the neuron's gonna fire if it's like above and below this threshold, or like they're gonna like use a logistic curve or like a tangent kind of thing. And then the idea is that like this, like in quantum mechanics, you'd just be like, oh yeah, multiply all these matrices together. But like in the neural network theory, there's a little non-linearity sort of like at each layer. And then, that allows it to express like somewhat like arbitrary functions.
So then is the upshot that consciousness is a quantum phenomenon? Is that
Well, I guess they were, well, I guess they were like the sort of, the
consciousness collapse of a wave function. There are professors who made their entire careers on that.
It's more like, neural networks have a certain dynamics, right? Like, there's going to be this kind of error function, and the dynamics are basically like minimize that error, and trying to sort of, I guess it's sort of like try to derive.
See, but what you're doing,
Matt,
what you're doing is you're equating math with reality, because a neural network can be approximately described by matrices, as can quantum physics. Doesn't mean that matrices are real. They're just a mathematical abstraction that at best only describes the phenomenon approximately. Because here you're talking about nonlinearities. And even quantum physics has nonlinearities.
Well, I mean, one thing that you would like, though, is I think in this that obviously, like, I don't even understand in this paper, like, in what sense, like, either quantum mechanics or general relativity emerge, in the sense that, it's just a bunch of fucking neurons or like whatever. Like, I didn't read it closely enough to be like, well, what's like the space supposed to be? Like, how's this actually?
No, it's an attempt. It's an attempt to describe mathematically something that we don't really understand. And until there's more physical evidence. But again, it's just a theory.
One thing you'd appreciate about it, though, is that they view quantum mechanics itself as like emergent from like a certain limit of the neural networks, and like not fundamentally like quantum. Like they kind of make a little reference to the Bohm theory and stuff.
Where can I?
I've often thought that it's
Where can I read this paper? Are you going to post this one?
Oh, yeah. Where did I even find it? I think someone's linked to it. I think I just saw it on Twitter.
Or do you have the link? Can you show us the link? And I could just, you just click on it.
Yeah. I think it's on the archive. Let me see. Maybe you can understand it more than me. I just looked through it quickly.
Well, you're smarter than I am. So if you don't understand it, I don't have a lot of hope for myself. But
I gave it like 10 minutes.
You're smarter and you're younger, so your brain works a lot better. You'd be surprised once you reach 30. Are you 30 yet?
Yeah, I just turned 30.
Well, it's all downhill from here, right, Matthew? You're the Matthew.
Oh God!
I know you're over 30. You got to be at least 31 or 32. Once you reach 30, your brain doesn't work anymore.
Oh gosh, you're giving me.
Is this it? How do I?
Yeah, I popped it on the chat.
Yeah, but I couldn't click on it.
Really?
Could you? Oh, is it still there? Let me see.
Yeah.
Oh, okay. Which one is it? Hey, Red Hat, or the other?
The first one is the second one. The first one's just the site with my notes.
I'm going to click on both of them because it'll make it easier.
I mean, if you're concerned about practicality in a way, I think that, we can understand a paper like this, which, it's making a kind of grand claim. But it's certainly true today that, like, if you're doing, even just, like classical simulations of like really complicated many body systems, and you're like, CS, young, computer literate grad student or whatever, like you're using neural networks anyway, or at the very least something like tensor network methods. Like, in other words,
well, it's the same as spin
up representing the whole fucking Hilbert space. So what if I had a neural network that you know, was able to like approximate, you know, these different wave functions in some limit. So they're already like starting to use, there's already like a kind of collision of, you know, physics and machine learning.
But there are,
Right? So it's like, I'm not making a claim like ontologically or like whatever. I mean, that's probably a bit much to say because this is just a metaphor. I mean, world is neural network. Right?
you know, there are entire groups that are claiming, well, particularly at the University of Arizona, and I forget the guy's name. He's a close associate of Deepak Chopra, who's another fraud. But they claim that consciousness, since we don't know what it is, they claim that consciousness is a collapse of the wave function.
Yeah.
And they got all this math, they got all this math that, you know, they think proves it. And it's just a crock of shit.
Yeah, I'm not so clear that we can't perceive superpositions. I mean, privately, like
Well,
I
again,
can
you know, I
entertain
don't
two
believe in
ideas
that.
at once.
Those of us
like,
who
I don't know.
subscribe to Bohm don't believe in superpositions and all that crap and probabilities. We don't accept that. Bohmian physics kind of does away with that.
Well,
I know you're still into that, and most physicists are.
Hey, you don't give up the wave function. I mean, there's the wave function still.
The wave function is not physical. The
Those.
wave function is an intermediate mathematical step towards some final measurement outcome. Bohm.
So you really view in Bohmian mechanics like the wave function as like emerging, like being generated by like the particles.
No, what you're doing Bohmian mechanics, and I thought I had explained this, it's an intermediate mathematical step. Yeah, Bohmian mechanics is derived from the Schrodinger wave function.
Yeah, that's all I'm saying, you know.
But the thing is, you solve Schrodinger differently to get a physical three-dimensional solution of trajectories, real trajectories of real particles, which give you, you know, real measurements that are not probabilistic.
Yeah. Well, but
not
I don't know what it means to say
probabilistic at the measurement
like
stage.
intermediary. Like, you know what I mean? Like, I could be like, oh, the electromagnetic field is just like an intermediary.
No, but that's real.
Like,
Electromagnetic field is real. You can measure it. You can't measure Schrodinger's. You know, Schrodinger's equation is solved in Hilbert space. Hilbert space is not physical space. It's a mathematical construction.
true.
So since the Copenhagen people didn't know what to do with it when they realized, hey, solution to Schrodinger's equation isn't giving us physical solutions, they had to come up with some kludgy, well, you know, Max Born came up with, well, these are probabilities, you know, if you square the coefficients, they give you probabilities. Bohm's approach was completely different because he solved the Schrodinger equation differently. And he came up with real physical solutions.
I guess, well, you know, we've talked about this before, but it just, to me, it's like when I think about Hilbert space and stuff like that, like, I don't, like, I know what you're saying when you say that it's a sort of
not real space, space.
But I mean, you know, you're, you know, it's like you start from like what we've been doing with spin, right? Like we start from a symmetry group, SU2, and we look at like unitary representations of it.
Yeah.
And, you know, those are states that live in this little two-dimensional, say, if it's just a spin half particle, two-dimensional Hilbert space. And it's like, yeah, like the Hilbert space, sure, it's like kind of like a mathematical intermediary, but like the point is that you've represented like the symmetry group that you're interested like on that space. And because you've used a unitary representation, it can be interpreted in terms of the probabilities. And it's just like you can do that for like whatever group you're interested in. So like I'm not disagreeing that it's sort of like a mathematical.
You know something? You talk about unitary representation, but the collapse of the wave function is non-unitary. So you have a dilemma right there.
Well, again, I mean, I subscribe to this sort of relational view that like collapse happens at the kind of interface, at the kind of like interface between two things, but that from a third perspective, measurement is just two things getting entangled. It's like if you measure something, yeah, you see a collapse. If someone else is looking at you measuring something, then it's like you guys get entangled. So that it's like a perspectival.
And what if you don't have observers?
Well, you always have interactions. It's just when
You have
when
interactions, not observers. Before there were observers, we had interactions.
if you were the thing being entangled, it would be like a measurement for you. And again,
Well,
you know, you can measure things, and I'm not talking about consciousness. I just mean like from your position in the world. You
well, consciousness
oh,
is a whole different.
yeah, it's
We don't know what consciousness is.
yeah, we don't.
You know,
I
although
agree with
people.
you there. Could not agree more.
But yeah, no, you know, we have a different perspective. You know, I'm more of a, you know, an empiricist, and you're willing to accept a lot of theory, I think, on faith. And also your philosophy is that you want the world to be probabilistic because
Well,
it makes things more interesting. I don't believe that.
you know, what we'll see today
Yeah.
is, you know, I was saying to Matthew before, I mean, it's, you know, this is one of my favorite little.
I think we're putting Matthew to sleep.
Oh,
Matthew must have had a wild night last night. Why all the yawning? Come on, you got to wake up for this. This is tough stuff. What are they doing in Jersey City? I don't know. Is the virus over?
Wow, you got a good memory too. Woo. That's all right.
The thing that I was going to talk about today is like one of my favorite things, and it, one of the things we'll see is the way that in this context, and I'm not saying it's able to be proved to be possible in all contexts, but in this context, you can sort of view like the views of one particle on another. Like if you were that particle, like what direction everyone else is in, as like in some sense more fundamental than its like position. And I'm like really fascinated by the idea. Maybe that's something that, you know, maybe I just have like a philosophical bias there. But when I think about, you know, things like quantum gravity, which, you know, I myself don't understand. It's like, you know, when we talk about how does space and time, you know, emerge from something more fundamental, one thing that makes philosophical sense to me is that it would like emerge out of individuals' views on the world, and that, you know, in general, those views can be inconsistent with each other, and then like in an appropriate limit, those views become consistent with like, oh yeah, we're all in 3D space or something. But like outside of that limit, it's like, oh no, we're in some weird ass, you know, it's got some fractal dimension or something. So, you know, I guess I just find that cool. Maybe that's bias, but maybe we should get started. Yeah, I don't know. Maybe some people got confused about the time because we're meeting a little early.
You know, I think we lost a few people. We had more than 4 people a little while ago, and now
true.
Down to 4.
There were those who promised to come, but again, yeah, I mean, you know, usually we meet at 4.
No, but we had about 5 or 6 when we were talking before, and now I don't know what happened.
I don't think we had 5 or 6.
No. Yeah.
We had more than
Jamie
4.
in here. Jamie's here. Hey, Jamie.
We had 4 or 5. You know, Andre, I know wanted to come. Yeah, he was confused last time, and I told him, you know, that I think you had updated Quantum Appaloosa had the right time, but I think that Meetup was not updated as quickly. So Andre lost track of the time. Yeah, maybe I'm surprised he's not here now.
Look, Moshe, I didn't notice this. Moshe.
Yeah, Moshe's not. Oh, he wants to Zoom. You know what it is? The Zoom link is correct, but you got to knock out. There's a piece that comes in there that you have to knock out. It happens all the time.
Why? Okay, weird.
Do you have Moshe's email, or should I send him?
Well, I just, yeah, I mean, Yeah, maybe I should email him too. I just posted the link on the. Oh,
I'm surprised to see him. He didn't even sign up for the meetup. We should call Andre and let him know it's on now. He's probably confused again.
Yeah.
Because he signed up and he's not here.
You can do that. I don't have his number.
Yeah, I don't have his number either.
Andre. Well, maybe we'll give it a second for Moshe to come.
You see what happens? Maybe you're not aware of it. When you click on the link on the website to the Zoom, when you click on the Zoom link,
oh, Andre's
the wrong URL comes up.
Really?
There's a little piece that gets stuck in the middle of the URL, and then it doesn't go anywhere. And I don't know why that happens, but I figured it out, so I know what to do to correct it.
Oh, you're right. There's like a little fucking...
Yeah, there's that little...
Oh, my God.
That thing. You see that?
God, that's horrifying.
I don't know why that happens. And I don't think your Meetup site is not the only place where it happens. It happens elsewhere.
Okay.
It's
well, that's good to know. I'm glad it's not my fault. All right. Crazy.
But you should check with Meetup and ask them why that happens. If they know.
The link looks fine, like right there. Like, if you...
It looks fine until you click on it, and then it's goes nowhere.
I tell you. I don't know. Well, while we're here, we may comment on...
Who is this dude?
I love this painting.
Is that what you're going to look like when you're 80?
Oh, yes. This is Michael Atiyah.
Is that Atiyah?
We talked about these, web of stories. It's like a great YouTube channel of...
Well, my father worked in the Sudan. In fact, his father worked in the Sudan before him, so long established. And so we lived in Khartoum, which is a rather small community as far as the sort of Western community is concerned.
I just love this guy, the way this guy talks. There's this great YouTube channel called Web of Stories of, elderly people basically talking about their amazing lives in the 20th century. And Atiyah has one of them. Yeah, and then I found this this painting, I guess, it's probably hanging in, I don't fucking know, Oxford or Cambridge or something.
But he's not British. What is his background?
He's
not Sudan. What? He's not Sudanese, although it sounds like an Arabic name.
British Lebanese.
Lebanese, yeah. Okay.
Yeah, it was like a couple of years ago that I sort of was reading about this very interesting conjecture that he made, which is what we'll talk about today. And yeah, he's a super interesting guy. He did a lot of work with stuff related to spinors and fermions, like both in physics and in mathematics. And I remember when he died not that long ago, I guess it was last year, there was all this hullabaloo because he claimed to have solved the Riemann hypothesis, like right at the end there. And, it was like, I think everyone's like, there's like a non-zero chance that he did it because it's Michael Atiyah, he's the guy. But was proof not accepted. There were flaws, so they say. But, so I put this great little...
I'm working on it, so it won't be long.
Yeah,
By the end of your presentation, I should have it done.
Yeah, right in the margins,
Right.
As they say. Well, I'll tell you, amazingly, we got Andre in here, we got Moshe in here, in theory. So maybe we should get started. Okay, so, all right, I'm sharing my screen. So before we get into it, I just want to review what we talked about last time, just the build up to this Barry Robbins sort of proof of the spin statistics theorem. Not the traditional proof, but an interesting construction nevertheless. So, basically, when it comes to the spin statistics theorem, like what you're trying to do is unify three ideas. On the one hand, rotations, on the other hand, permutations in the tensor product. And then on the third hand, like actual swappage in space or whatever. You know, we know that people always say, yeah, you know, bosons are permutation symmetric particles with integer spin, and fermions are permutation anti-symmetric particles with half integer spin. And, you know, that actually requires some more assumptions than what we've talked about so far. You know, we have, in the case of integer versus half integer spin, this particular behavior under rotations. In other words, if we have half integer spin and we rotate it 360 degrees around some axis, it's going to pick up a negative sign. But for an integer spin, it's not. And this has to do with the fact that we're using, you know, SU2, the double cover of the three-dimensional rotation group, as opposed to just the rotation group itself. So, you know, I showed this little demonstration of this last time. Here we have a spin half particle. And after one rotation, up here you see the phase was the negative of what it was at the beginning, comes around again, and after two rotations, it's back exactly to where it started. And, you know, rotate it around again, oh, negative, pop it around, and so forth. If we do the same thing with a spin one state, then, you know, we got two stars, and after a single rotation, we come back to where we began. And, you know, if we keep going along that little road, we hit up, you know, spin three halves. After one rotation, we get the negative. And then after two rotations, we're going to get the positive. Boom, there it is. Okay. So that we have this idea about how spin states transform under rotations. And, you know, it's like, suppose we were just working with XYZ coordinates and with the, you know, normal rotation group, you know, this wouldn't even make sense, because all we would be keeping track of is like the XYZ coordinates of the point, and we'd be like rotating that around. But the useful thing about using, hey Moshe.
Hey.
I'm just giving like a little review of last week before we get started. So half integer spins come back, get multiplied by -1 under a rotation, a full rotation. Integer spins come back to themselves after one full rotation. And as I say, you know, if we were just using the normal rotation group and we're like rotating, you know, real XYZ points, it's like this couldn't even really happen. Only because, you know, we're working with spinners / spin states or whatever, which are defined only up to phase, that this is even like a thing that we can represent. Okay, so we have rotations. Now, we want to combine the idea of rotations and like a permutation in the tensor product. And so this is what we saw last time. We employ the oscillator representation of spin. So as you recall, for each spin, we second quantize a spin half state. In other words, we introduce two harmonic oscillators, one corresponding to like the up basis state, the other one corresponding to the down basis state of like the basic spin one half representation. And you can think about this as like the oscillators keeping track of like the number of up or down quanta. And, you know, when you look at, you know, this Hilbert space, it decomposes into sectors corresponding to different J values of spin. So you have like a spin 0, a spin half, spin 1, spin 3 halves, and so forth, sector. And so, you know, by sort of taking the square root of a spin, in other words, representing it as two harmonic oscillators, not only can you represent a particular spin with a particular J value, but, you can describe superpositions over J values, changing J values or whatever. It's a more flexible representation. Now, in the case where we're considering like two spins, we introduce two harmonic oscillators for each spin, 4 in total. So, we know from before how to like second quantize an operator. So, if we had some basic spin half operator like this one, the Pauli X, we could second quantize it to act on this oscillator space by kind of wedging it in between like a row of creation operators and a column of annihilation operators. So, you take this, these are matrices, but, you just work it out like as if they weren't basically, and you get this linear combination of creation and annihilation operators, or this expression, let's say. This guy is going to act like Pauli X. In other words, it's if you upgraded a spin state into the oscillator, looked at its XYZ expectation values, and then you looked at these expectation values, it'd be the same thing. You exponentiate this, you do an X rotation. So we're able to like represent the Pauli matrices on the oscillator space using this sort of classic way of, second quantizing, where you're thinking about it like we're sort of, associating like each coefficient or whatever, each matrix element with a certain combination of creation and annihilation operators. Okay, so, this gives us the XYZ operators for the first spin, let's say spin A. Then we can do the same thing for the spin B. That's fair, okay. Nothing weird going on. But, you might be like, well, we got 4 oscillators. So, what's stopping us from kind of joining up the oscillators into spins in a different way? In other words, why not make a spin who's composed of like the 2 up oscillators, across the original spins, or a spin created out of the 2 down oscillators of the original spins? So for example, here we just play the same trick, but here we have, creation operator for, the up quanta of spin A and the up quanta of spin B. And here we have the down ones. And similarly, we can get, these XYZ guys. Then we look at what happens if we do a rotation, say like a Y rotation, simultaneously, like use this Y operator and this Y operator, and we do, a rotation, say, of theta degrees, or say pi degrees around the Y-axis of these so-called cross spins. And if you look at what happens to the original spins, they swap places in the tensor product. And, the really cool thing is that when this happens, if the original spins were half integer, then it picks up a -1. And if the original spins were integer, it doesn't. So, we seem to have, to some extent, unified rotations and permutations. So here, here, I'll just do it again. So what this is, if you just observe, okay, this arrow is moving from the blue to the red. This is doing just a pi rotation simultaneously around the z-axes, the y-axes of the cross spins. So we have spin, A is blue and spin B is red. You can see that, it's expected rotation axis here, these sort of white or gray arrows. For, ease of like noticing that they've actually swapped places, I've put, the original locations of the spins, which I just arbitrarily decided start in a separable state here. So the original, direction that blue is pointed in is this blue dot. Original position that red was pointed in is this red dot. So, you know, as I run it again, you know, you'll see, okay, we start off blue is blue, and then after pi rotations, blue is red, and red is blue. Moreover, in the middle, you can see the phase of the overall wave function, and you can see the original, here, I'll do it yet again. The original phase is in yellow, and the current phase is in white. And you can see at some point during this rotation, it flips, and it goes to the negative of itself. Moreover, basically yellow and green here are the two cross spins. So like this is the guy, that the yellow guy is like the one like made out of like the two up oscillators of blue and red. And this is a guy made up of like the two down oscillators. What I'm gonna do now is I'm just gonna like have it just evolve kind of forever. I'm just gonna like not restrict myself to just a pi rotation. So what this is gonna do is it's just gonna like sort of bounce back and forth. So I'm gonna do it again because those states are kind of close to each other, so it's a little difficult to see. All right, that's nice. That's a good one. That's a good one. All right, so you know we do a swap, we pick up that negative sign. Now we're coming back, full rotation. Oh, back to where we began. Meanwhile, you know, if you look closely here at what this little dude is doing, you see, like, look, like on the cross spins, like this amounts to just a little Y rotation. Like Y is the, you know, up here in this, you know, visualization. And you can see that this little tiny little baby arrow here is just swinging around the Y axis. And so is this guy. But one thing I want to note in this connection is that, like, whereas the two spins that we started out with are both spin half, that's not necessarily the case for the cross spins. In other words, the J value I've represented by like the radius of the sphere. And you can see that like in general, like these cross spins are gonna have like, in this case, it's like greater than a half J value. And this is like clearly like less than a half. And so, you know, this is sort of brings up the importance of like using this oscillator representation. In other words, like to do these sort of exchange rotations, so-called, you can't restrict yourself to just the usual Hilbert space of like two particles with a specific J value tensor together, but actually need to work in this sort of like larger Hilbert space, sort of like rotation, kind of like takes you out of the original Hilbert space into this sort of extended one, which, you know, in some of the papers, they sort of like, think about it like the space in which the spins are sort of parallel transported. You know, we'll sort of maybe try to talk about that a little more later. So, okay, so we have that, but like, let's check out what happens if we start with a spin one state instead of a spin half state. So here we can see after a pi rotation, the phase is not flipped. And in fact, in this particular instance, we can see the phase isn't really doing much at all. And so, you know, that's the first cool thing. We, by using the oscillator representation and building these sort of spins that are built out of pieces of the original spins, we can, you know, in this sort of natural way, unify the idea of a rotation and a permutation of the states in the tensor product that has properties quite like what we'd like from a spin statistics theorem. In other words, half integer particles, when they're swapped, they pick up a negative sign, and integer particles, integer spin particles don't. So, okay, so there you go. That's basically a summary of what we talked about last time. And as I say, you know, if you're interested in this stuff, here's, you know, some papers, some links to papers to get you started. So, you know, where we left it last time though, was just there. You know, we sort of unified rotations and permutations, but, you know, in a way that's not enough, right? Because, you know, we also want to consider like actually like taking the particles and like exchanging them, you know, in space. Like, in other words, we're dealing here with just the space of spins and maybe, you know, a sort of extended space in which we can parallel transport or something, the spins, but we're obviously not dealing with their positions at all. Is there a way of doing that? And so that's what we're gonna see. And we're gonna see it's like a sort of essentially kind of classical or almost like semi-classical kind of thing. But one that's like kind of inspiring, okay? And it is related to this conjecture of Atiyah's. So, all right, we begin. All right, here's the fun part. Fun begins now. So we're gonna begin from this following observation. We can build up a basis for n by n Hermitian matrices that looks like this. So suppose n is 3. We have 3 matrices each with a single 1 along the diagonal. Then we have n times n minus 1 over 2 matrices that look like this. And then we have another set of matrices that look like this. Like, given here, you know, the rule for the components. In other words, you go over, you know, sum over, or, you know, iterate over I and j, and look for I is less than j. And like for these matrices, then like in the ijth component, you put a 1, and in the jith component, you put a 1 as well. And here it's the reverse. Well, here it's the same, but you put an I and then a negative I. So you get, you know, n squared matrices, and they form a basis for n by n Hermitian matrices, so that any such Hermitian matrix can be like decomposed as like a sum. In other words, like if you take the trace of, you know, one of these matrices, each of these matrices times a Hermitian matrix, then that's like the component in that direction. And if you multiply that by like that Hermitian matrix and you sum over all the Hermitian matrices, you get exactly the original Hermitian matrix back. When you do this, you get like a real vector space. In other words, like these components in this basis are going to be real numbers. And if we allow them to be complex, we get the n by n unitary matrices, which, as we know, arise as exponentials of the Hermitian matrices. Okay, but like if you look at these, one thing that might jump out to you is that, they seem reminiscent of the Pauli matrices. In other words, if you look at this little block here, I mean, that's just like 0, 1, 1, 0. I mean, that's just like Pauli X, right? And, over here, this block, that's just like Pauli X, like down here. And in a way, like this is like Pauli X, but like where, it was built out of like this component, like the upper, upper left-hand component, upper right-hand component, lower left-hand component, lower right-hand component. And similarly over here, this kind of looks like, okay, we got Pauli Y stuck over here, Pauli Y stuck over here, etc.
What happened to Z?
So, right, yeah. So for Z, instead of having Z, we have like these diagonal matrices, but clearly we could build Z out of linear combinations of these. In other words, I could build a Z operator by just taking like this matrix minus this matrix, and then I would get Z. And in fact, we're gonna do that, totally. So, another way of saying like how to get these matrices is, say, like to take Pauli X and be like, all right, iterate over I and j, look at for I is less than j. And then like the ith component of the matrix is going to be like the 0,0th component of Pauli X. The ijth component is going to be like the 0,1 component of Pauli X. Ji is going to be the 1,0 component, and jj is going to be the 1,1 component. In the original, you know, just for comparison, you know, in the original paper, look at that. Oh, actually, is it in here? Oh no, it was in the, I mean, they talk about it here, but actually, I believe what I'm thinking of is in this guy. I just want to show you this because it's a little more visual.
Matt, are all of these links in Hey Red Hat?
Mm-hmm.
Okay.
So here is what I wanted to show you. So like, suppose sigma here is like Pauli X, and the indices are like, you know, referring to the 4 components of Pauli X, you know, 1, 1, 1, 2, 2, 1, and 2, 2. And then, you know, we go over like I and J, and, you know, the idea is that like, this is like the ith component of this big matrix, and we put, you know, the 0,0 or the 1,1 component of Pauli X here. So, you know, this gives us basically what we have here concretely. And, you know, that makes clear what I just said about getting those Z matrices, you know, as linear combinations of the diagonal ones. We could just do the same thing, you know, where, where, you know, the sigma here could be Pauli X, it could be Pauli Y, it could be Pauli Z, or whatever. And, you know, we're sort of distributing the components, you know, in this sort of symmetrical way around this matrix. So, you know, if we do this, we build up these sort of XYZ matrices, then, you know, it's clear just from their construction that, you know, they're each with, you know, each triple of them is going to satisfy the angular momentum commutation rules, and each set of XYZs is going to commute with the other XYZs. And, you know, we're going to think about these ultimately as doing our exchange rotations. So, you know, sort of just to show you the calculation, like for example, you know, this is some code here which generates these basis matrices for the n by n Hermitian matrices. In other words, here, we're making up the diagonals, the ones that are kind of like involving Pauli X, the ones kind of like involving Pauli Y. We generate like a random Hermitian matrix. We can decompose it into some components, which you can see here. We just go through all the matrices, multiply each one by the Hermitian matrix, take the trace, we get these guys. And then we can get the Hermitian matrix back by just multiplying each of those coefficients by, you know, the corresponding Hermitian matrix. You know, and if this was like unitary, then, you know, those coefficients or components or whatever would be, you know, imaginary. And in the case that they're Hermitian, they're real. So there you go. So in short, we begin by describing this basis for n by n Hermitian matrices, which is kind of like built out of, in this funny way, Pauli matrices. So that, you know, even though we're talking about, you know, n by n Hermitian matrices or like whatever, we can associate with each like ij a set of XYZ operators. That's the first thing. It's the first thing. Now, suppose we have n classical spinners. In other words, I just mean some spinners, like not quantum at all. Remember, like a spinner, two complex numbers, you know, it represents like a rotation axis, as we well know. You know, we can do our trick with the stereographic projection, or we can take the expectation values with X, Y, Z, get a direction. It's got a phase, and like rotating this phase doesn't change the direction. And then in the case where we're treating the spinners classically, you know, we just are like, well, you know, in quantum mechanics, like the norm of like the spinner would have to be 1. So probability sum to 1. But if we're just dealing with it classically, we'll let the norm be anything. And that would just mean that this, you know, representation of a classical spinning object might be rotating faster or slower. So like the length of the rotation axis represents the, you know, speed. Now, that's, you know, classical use of a spinner. So if we have n classical spinners and we want to like treat their states as a whole, you know, to combine them, we don't use the tensor product, right? Like we would use the tensor product if we were dealing with like some spin half particles and et cetera, et cetera, et cetera, but we're not. We're just treating them completely classically. And so we stick to the old classical way of combining systems. And what that would involve is just sticking them together, you know, no tensor product at all. In other words, if we had 3 spinners, you know, each with like 2 components, then we could stick them in like a column vector like this. You know, it's just a concatenation of them. We got, you know, the 2 components of the one spinner, and then the 2 components of the other spinner, and then 2 components of the third spinner. So these dudes live in a 2n dimensional vector space. Now, we could build up, you know, Pauli matrices that act on, you know, each of these spinners in a pretty obvious way. In other words, just as like block diagonal matrices. Kind of trivial in a way. Like we could just, you know, get our XYZ operators on these like individual spinners and then, you know, whatever. But, you know, we want matrices and like act on this 2n dimensional space. So for example, here, like the XYZ operators that act on just the first spinner, they're just like block diagonal, you know, here. So they just sort of act on the first 2 components of this vector. And, you know, we can use them to rotate, you know, just like this first spinner here and like, you know, get the XYZ expectation values, whatever, if you want to think about them as expectation values here. At the very least, you know, you can extract the rotation axis. And then, you know, for the middle spin, you know, we got Z, I don't know why I put it, ZXY, yeah, I guess, okay. ZXY, you know, for the middle spin, and then Z, X, and Y for the last third spin. And obviously, kind of like just like before, you know, these matrices in each of these sets satisfies the usual, you know, angular momentum commutation relations, and they commute with the operators in the other sets. So there's much to say, you know, we could rotate these spinners individually without affecting the other ones and easily extract their rotation axes and so forth. So, you know, again, we're living in a 2n dimensional space, and these operators obviously are 2n by 2n dimensional. Okay. So now here's the punchline. Before, we were dealing here with these n by n matrices, and we had these sort of, you know, Pauli matrices that we sort of like built here. Here we have some 2n dimensional matrices, you know, related to the Paulis, okay? So here's the thing. If we take these operators from before over here, these guys, call them the EMs, they're n by n dimensional, we can upgrade them to act on this 2n dimensional space by just kind of doing the retarded thing of tensoring them with the 2 by 2 identity. Just like, so going through each of those matrices and just like tensoring them with the 2 by 2 identity. And if we do that, then these matrices generate the exchange rotations from before, but now in this sort of classical setting. In other words, instead of talking about quantum spins, we're just talking about classical spinners. And, you know, these, say, if we take like the, you know, these three spins would be, these three spinners would be like the, you know, the original spins from before. And we can get their like rotation axes or whatever. And then if we wanted to do an exchange rotation, say of like these two guys, what we would do is we would like look at the, you know, the E01 X matrix. And that would rotate, that would like permute those two spinners. We also get this sign flip because it's also a rotation. So we can just take a look at that. So this is like very much like what we saw before. We have, so we're doing a pi rotation. We have two spinners, which are represented here in red and blue. And we can see that after a pi rotation, you know, the red spinner, which had been pointing here, is now pointed here in blue. And the blue guy, which had been pointed here, is now pointed here at red. We, you know, chose as our matrix to evolve under this one, in other words, the one that I said before. So the, where ij is 0, 1. So we're like exchanging between the 0 and the first spinner. And we chose like the y version of it. We exponentiate that. Here, at the top here, what I do is I take the XYZ expectation value of the exchange spinner, basically. In other words, you know, say, maybe I should have written these out. You know, remember, these are the n by n matrices, so we have to tensor these with the 2 by 2 identity to get the 2n matrix. But say, you know, I take the expectation values of like the Pauli Z operator built out of this X1 and this Y1 and so forth. And you can see that what happened is like, just like before, the exchange spinner just rotated 90 degrees around the y-axis while the two spinners here rotated. Moreover, if you look at the phase here, because we're dealing with the classical spinners, we're not like really paying attention to the overall phase. We're paying attention to like the relative phase between the two spinners. And you can see that the phase of, yeah, is that, okay, let's do another one so it's a little easier to see. That's sort of confusing looking. So we're doing our rotation. Okay, so the main point is that this arrow here, this yellow arrow, and this purple arrow are opposite to each other. In other words, this is the red guy. Red guy started out with this phase. Red guy got swapped over here. You look at it, this guy's now pointing in the red direction. And if you look at his phase, it's exactly opposite to the phase that he like started out with. So the relative phase between these two guys is, has been flipped. And this is just down here, like the overall phase, which is like not that relevant here. Okay. So, I'm not sure, okay, does that make sense? I mean, what I'm saying? Maybe it'll become more clear if we talk about sort of like the relationship between this classical model and the quantum model that we had before, right? So like before we had this quantum model, we had n spins and we split each one into 2 oscillators. Here, we're dealing with n spinners who live in a 2n dimensional space, okay? So we can recover the the quantum picture from this classical picture through just sort of second quantization. Like, in other words, if we have n spins, we have 2n oscillators, which is exactly the same number of dimensions as the space of spinners. So like if n is 3, we have, 6 oscillators. So like here's the annihilation operators here's like this, for the 0 spin we have up and down, for the first spin we have up and down, for the second spin we have up and down. Then given, say, like a 6-dimensional state of 3 spinners, a classical state, we just have the 3 spinners, they're each 2-dimensional, we stick them together, 6 dimensions. We can just second quantize that into like a raising operator by multiplying each of those 6 components by each of these 6, say, creation operators, that take the adjoint of these, and then summing, just like we've been doing. And, that operator will like raise the second quantized, state like out of the vacuum. And, that quantum state will match the original classical state that you started out with in its expectation values. Furthermore, we can quantize these 2n by 2n matrices by just like we were doing before, wedging them in between a row of creation operators and a column of annihilation operators, or in other words, in terms of the components, just taking this sum here. And, if you think about it, like if you sort of work it out, it's like, this is no different from what we really were doing before. In other words, say, like look at this guy, right? If you think about what this would be like in a second quantized context, it's like each of these 6, columns or like in rows or whatever, like they're labeled by the oscillators, So we're considering here, the first 2 oscillators. So that's just like the first spin. And, we're going to end up with like a linear combination of like the down oscillator and like the up oscillator, like whatever. And that's just going to give us exactly what we had here. It's just going to reduce down to this. So, in terms of these matrices that act on these spinners, we get exactly like the same thing we get from just this argument here, where we just like second quantize them individually. If we then look at, what happens when we second quantize these operators, which again, remember, tensor this with the 2x2 identity. In fact, I'll print out a little thing, you'll see what those matrices look like. It's just another way of saying this. They act on oscillators across the original spins. Yeah, so just so you see like what they look like. They're gonna look something like this. Right, yeah, better example. So, this is just taken the, one of these guys up here, the X guy or whatever, like one of these, And, you know, when you multiply it by the 2 by 2 identity, you know, you get something that looks like that, just for concreteness. Okay. So the point is to put that back where it was. Okay. Point is, you know, we started off with this sort of quantum model of an exchange rotation. And now we've actually developed like a classical model. And we have this way of sort of upgrading or quantizing the classical model in such a way that, you know, make sure that we have the same results on both sides. We can think about this 2n dimensional space of spinners where we have both the ability to like rotate the spinners, but then like also do these exchange rotations like across the different spinners as essentially, you know, acting on the space of creation annihilation operators of the quantum version. In other words, we're dealing with a 2n dimensional space, and we have 2n creation / annihilation operators for the oscillators corresponding to those spins. So, you know, this is sort of like a way of, you know, formalizing a little bit better these rotations and then also the exchange rotations. Now, one interesting thing, you know, if you looked at this, do it again, is that, well, you actually, that's a bad example there. Do it again. So, you know, as this is happening, like notice that like the norms of these spinners is changing. Like in the end, because they start with the same norm, they end with the same norm once they're swapped. But in the middle, in between, you know, the norms are varying, which, you know, classically you could interpret like, you know, they're spinning at a different rate. But of course, it's interesting to think about the fact that in the quantum case, you know, if these start out in separable states, and like if that rotation axis is like, you know, somewhere in the interior of the sphere, it means that, you know, we're now dealing with a mixed state. In other words, an entangled state. So that it sort of makes sense. Like if you're like sort of halfway through like permuting the locations of these two spins, you know, you're going to be in this like entangled state. So that's kind of interesting. And like I say, you know, if you start out with some state of like classical spinners and whatever, and then, you know, second quantize it to like a state of like n spins built out of these oscillators, and, you know, you take some exchange rotation that acts on the spinners, and you second quantize that to an operator that acts on the quantum guys, and you apply it. And then you look at the XYZ expectation values in the classical case and in the quantum case, they're going to be exactly the same. And I'll note that, like, you know, if you're trying to, you know, like actually get that result in general, you know, you can't do what we've been doing, which is just sort of like approximating the harmonic oscillators by like truncating their dimensions at some point. You know, max energy is like whatever. You know, in general, like to get that exact result, you got to really treat the harmonic oscillators in the real way. In other words, have you know, any number of excitations, you know, and work with, you know, the infinite dimensional Hilbert space that results, take a bunch of integrals, you know, your computer will hate you, and, you know, but you'll find, and, you know, if you're kind of interested in that, you can look at this code here, which does it very slowly, but it does it. Okay. So with that, we're sort of going to turn to kind of like the punchline in a way. Because we're this sort of classical picture of the exchange rotations is going to allow us to sort of touch ground, make a connection between, you know, the exchange rotations and like actual swaps in position. This is like the really cool thing. And this relates to the conjecture of Atiyah. Okay, so here's the idea. Suppose we have n points arranged in 3D. We imagine like a little sphere around each point. We then connect up each point like with a bunch of lines, you know, connecting the centers of the sphere, each sphere to every other sphere. And we add a star or whatever, a point, to each sphere at each intersection with one of these lines. So if we had, you know, n points to start off with, we're going to get n constellations, one for each point, each with n minus 1 stars. In other words, if you had 3 points, you're going to get, you know, this guy's going to have a constellation of 2 stars that are basically going to tell you the angle that like this guy's in and that guy's in. Like this guy's going to have a constellation of 2 stars. That's going to tell you the angle that those guys are in. And this guy's going to have a constellation of 2 stars. That's going to tell you what angle the other guys are in. And naturally, you know, these constellations are independent of the distance between the points. Only the relative angles are encoded. And furthermore, you know, one can observe that like any 2 of these constellations is going to have 2 stars that are pointed in opposite directions. Well, we know what to do with, you know, n minus 1 stars or whatever, you know, we have a constellation. Well, we can use our favorite thing and, you know, form a degree n minus 1 polynomial where we take those points on the sphere and, you know, stereographically project them to the plane, get some complex numbers, and those are the roots of the polynomial. Or better yet, you know, we could work with an n-dimensional complex vector in, you know, the j, in this case, n minus 1 over 2 spin representation. In other words, we could, for example, form an n by n matrix like this. So, you know, if we had 3 points, then we have 3 spheres, each has a 2-starred constellation. So it's like a spin 1 state. So we can associate like a 3-dimensional complex vector with each of those 3 constellations. And, you know, those vectors are 3-dimensional, there's 3 of them. And so we can form a 3 by 3 matrix where the columns are the components. So this column, you know, represents the 2-starred constellation of this guy's view on the other 2 guys, the angles that these other 2 guys are at. This guy, middle guy, this column represents a constellation of 2 stars, which represent the view of this guy on the first and the third, and so on. So, you know, the conjecture of Atiyah's is that, you know, like the determinant of this matrix will always be non-zero, basically. In other words, that these vectors will always be linearly independent. Kind of interesting. And like numerical evidence, like strongly suggests that's the case, and there's like certain specific cases where you could like prove that's true, but you know, for whatever reason, no general proof exists. So work to be done. But, you know, we're going to proceed as if it's true, and we'll see what happens. So from a configuration of endpoints I just want to check something. Okay. So from a configuration of endpoints in 3D, we can obtain an n by n matrix whose columns correspond to the mutual views, you could say, of each point on the others. Okay, call it V. Now, you may know that any complex matrix can be decomposed via the polar decomposition into a product of a unitary matrix and a Hermitian matrix. So you can think about this like decomposing a linear transformation as like a rotation and like a stretch or a shrink. So we can apply this polar decomposition to our matrix V and just take the unitary part, okay? And we get this like unitary n by n matrix. But then we do exactly what we did before. We had an n by n matrix. We just tensored it with the 2 by 2 identity. And then we got a 2n by 2n dimensional unitary matrix. So we've got, you know, this matrix, call it W. It acts on the space of n spinners, specifically this like exchange part of it. The motivation, where was it? At some point I said that up here, I sort of neglected to, here. What we're trying to do is, unify the idea of rotations, permutations, and the act of exchanging the positions of the particles. And so like what we want is somehow the act of dragging two particles around each other, switching their positions, to correspond to a permutation of the tensor product of the spins, which is also an exchange rotation, like picking up the proper sign. So what we would like, what would be interesting, is if there was somehow like a smooth map from the positions of the particles into the space of exchange rotations. And that's basically what ATIA is providing for us here. In other words, we start with like a configuration of endpoints in 3D. We get the mutual views, which are constellations, of each of those points on each other's, on the other ones. In other words, the relative angles. Each of those we treat as like a column vector in this matrix. We take its unitary part and we tensor with the 2 by 2 identity. And we end it with a 2n by 2n dimensional unitary matrix that acts on the space of n spinners, specifically like not the part that has to do with like the individual spins, but the part that like exchanges the two spins. And clearly, like permutations of the positions of the particles are going to lead to permutations of the columns of this matrix. Okay, now there's like a little technical detail that, I have to bring up. But let me just show you kind of what this looks like before I do that, just so we get a concrete sort of picture. Okay. One second, please. So let's just do it like, so start, let's just do that. Let's do like 4, and let's do like that. Okay, I've done this so that there's like all sorts of like little things you can, change. Actually, too much. Let's just do 2. Let's just do 2 of these guys for now. All right, so we have 2 guys, 2 spinners or whatever. Brown and purple, okay? So we see their rotation axes, which starts off with purple pointing at purple and brown pointing at brown. And we have the phase here. And the original phase, I guess I've represented in, oh, actually, let me, the original phase is gonna be in yellow and the current phase is gonna be in magenta. Gonna change it a bit. Okay. So, all right, so that's the meaning of that. We have the spin axis of this guy, spin axis of this guy. We have their phase. But then we also have this point here. So the white like stars or whatever, like these are the constellation, like that has to do with the position. In other words, if I take this green guy here and I move it around, you can see that, the constellation is changing. In this case, there's just 2 spins, and so they each have just like 1 constellation. So you can see like, as I'm like dragging this guy around, you know, as the constellations, as their mutual views are changing, you know, the rotation axis is changing, like the norms of these vectors are changing, the phase is changing. Okay. What happens if we like drag this guy, you know, around this guy so he's on the other side? We can see that like, lo and behold, they've permuted. You see over here, this guy's pointed in the green direction. This guy's pointed in like the, whatever the fuck that color is. And we bring them around each other and like, look, now this guy's pointing the green direction. So actually what we've been able to do is create like a smooth map that allows us to kind of like change the positions of these guys and, you know, swapping their views, swapping their relative angles, swaps their spin states. So, you know, we can even do this with like, let's say with like four spinners. So actually, I'm gonna do it again because those colors are kind of all like very similar to each other. All right, that's fine. So, all right, we'll look at this guy. You know, each constellation now has like 3 stars. In other words, this is like this guy's views of these 3 guys. Like these are the angles that these 3 guys are in. All right. So, you know, we start off and this guy's rotation axis is pointed at like this dark green dot. But what happens if we like permute with this guy? Holy shit, look, now this guy's pointed in this like maroon direction. Because now this guy's in the position that the maroon guy was in. And the maroon guy is like pointed in the green direction because he's now has the view that the green guy did. We like continue our little journey here. Now this guy's pointed, it's a little hard to see, I guess, pointed here in this purple direction. Purple guy's, you know, now pointed in the maroon direction. Maroon guy's pointing in the green direction. And finally over here, this guy's now in the position that light green guy was in, has exactly his constellation, and so he has the same view. So that's pretty fucking amazing. Like, you know, like, think about that for a second. So, okay, so now we've just sort of, I've got like 3 spinners and I've just sort of scattered them randomly in 3D, like I said, having them on a line. And, you know, now they just have these, you know, again, the white guys, these are the constellations. You see like this, these white guys are opposite to each other, opposite to each other, opposite to each other. The color guys represent, you know, the starting rotation axes of like the red, green, and blue guys. And, you know, if we take, you know, this blue guy and we, well, see, the problem with doing this is it always ends up, you know, if they're not in the same plane, it becomes a little tricky. Working with the, making it easier. So, you know, the point is that I can drag these guys around and the constellations are changing. And it's like by choosing the initial configuration, it's like I'm encoding an association between like a certain view, like a certain constellation and a spin state. And then if I drag the particles around each other, it's like to the extent that, you know, the particles swap views, they've also swapped spins. So it's like in a way, you know, you can think about this like a model of of indistinguishable particles in that sense, right? They don't have an identity of their own, right? So if we like, again, like take two of them, it's like through the starting configuration, which I'm going to come back to in a second, it's like we've associated like, all right, this constellation with this spin state or spinor state, let's say, and this constellation with this. And, you know, to the extent that we swap the views of the two particles, right? Like before, this guy had, you know, one star to the right, and this guy had one star to the left. Now the situation is reversed, and because they've swapped views, they've also swapped spins. In other words, now this guy is pointed in the green direction. And we can do this in like a smooth, continuous way. In other words, I can sort of like do like half a rotation here. And, you know, now I'm kind of like in the middle of the two. And I can, you know, just sort of arbitrarily drag this guy around. And, you know, in general, to the extent that, you know, so yeah, like, so, you know, in a way you could think about it like the view of a certain guy at the beginning becomes like a kind of coordinate for its rotation state. And to the extent that you rearrange the particles and like now this, from this vantage point, this other guy has this particular view as his constellation, then he's gonna have, you know, whatever spin state corresponds to that view. Okay, now I'm gonna mention sort of subtlety. So, you know, we start with n spinor states, and we can get this transformation associated with their n positions, call it W. Again, you know, we take the n points, get the constellations, which represent their mutual views on each other in 3D. It's a constellation of n-1 stars, and we associate it with like a spin state, right? That's like, say, you know, n dimensions. And so we get a 3x3 matrix, and then we take its unitary part, and then we tensor it with the 2x2 identity. And we get a unitary matrix that acts on, you know, 2n, the 2n dimensional space of the spinners. So, you know, to visualize this, like, you know, I sort of had a choice, right? I could, you know, I choose some positions at the beginning and I choose some spinor states, right? And I could begin by applying W dagger to psi, where psi is the 2n dimensional state of the n spinners. And then I could like allow one to drag the spheres around, changing their positions and thus changing their views, so that at each moment we have a new matrix W. And so that at each moment we could take W times psi and then like visualize like the resulting spinor states at each location. And, you know, this is a way of like encoding like an initial association between positions and spinor states, because, you know, at the beginning of such a simulation, like before you've like moved any of the spins at all, we just have, you know, we started off by applying W dagger. At each moment we apply W. If you haven't moved the positions at all, that's just W times W dagger on psi, which is just psi. And so, you know, this allows us then, you know, once we do change the positions, to examine, you know, the effect on the spinners. But, you know, there's actually, you know, there's a sort of like a choice here, right? Because we could have started by applying W to psi, and then when the positions are updated, applied, you know, W dagger. And I note that they just sort of have like slightly different effects. Like, I don't know, like they didn't really mention this in the papers I was reading. You know, this just might just sort of be an artifact of this way that I am visualizing things. But it's sort of interesting to think about. So in this latter case, that's what we were seeing before. So, you know, we start off with the view, with the different views, we get the matrix, we multiply it by, start off by multiplying psi by W, and then at each moment multiply psi dagger. And and what happens is just what we saw. When we swap, when we swap the views, we get a swap of the spinor states. So here, you know, as we saw, we have tan and gray or whatever. We swap, and boom, clearly the spinor states are also swapping. But note, the phase is also swapping. In other words, we get like an exact swap. Like here we start off, you see like the phase is pointed there. This guy, and the phase is pointed there, that guy. And then when we bring it down over here, we see that this guy, his phase is pointed in the direction of this guy's phase originally. And this guy is pointed in the direction of this phase. In other words, like what we originally wanted out of our exchange rotations is to get like, you know, like a sign flip when we do the rotations. And that sign flip isn't showing up here, even though these like rotations are like, you know, these swaps are working out for us. So, okay. On the other hand, if we start, you know, if we do the opposite thing, in other words, if you start with W dagger, and then at each moment apply W, you do get the sign flips, but there's like some sort of like little conditions, which I will show. So here, you know, as I say, we got these particles. All right. So now we're doing it in the other way. So we start off here, and notice that, right? So notice that, you know, where this guy's phase starts out. He's pointing in this direction over here. We swap the particle over here, and, you know, now the spinor states have swapped, and also the phase is the reverse of what it originally was. But this is perhaps a technical point, but whatever, it was bothering me at least. So yeah, is it even doing what I'm saying? I just full of shit here. Well, it's certainly doing the rotation, and the permutation. I mean, basically, just depending on how you encode the initial conditions, you get this slightly different effect. So like, for example, if I, you know, instead have these particles arranged along like the x-axis, you can see that a rotation swaps the sign. So we come over here, you see this arrow is pointed the opposite of this arrow, but, you know, we're not doing our exchange at all. On the other hand, if the particles had been arranged along the z-axis, that's what we had before, then you would get the exchange. In other words, if you encode the initial conditions in this like other way, it's like you'll get the exchanges in a way that like depends on, that actually like depends on in a way that what you've chosen to be the XYZ axes, which is like not good. Like, you know what I mean? Like obviously overall XYZ directions is somewhat arbitrary, you know? So like in the original paper, Berry and Robbins consider, you know, exchange rotations specifically like around an axis that's like mutually perpendicular to the Z axes of the spinners and like the line connecting those points. So like the Z, whatever you've chosen to be Z for the spins and the line connecting the points, that forms a plane. And then like, you know, you're doing your Y rotation like in that plane or whatever. You know, using the second method where, you know, we start with applying W dagger and then W, you know, it's like, obviously we could, you know, choose our XYZ kind of arbitrarily. So it's like, you'd always take, you know, two guys and just be like, oh yeah, well, wherever his star is, and then this guy's got the opposite star, they could just be like the Z plus and Z minus direction or whatever. And then, you know, you'll get your exchange and your sign flip or whatever. Okay, kind of like a random technical point. So let's just get back to the sort of like philosophy of it. You know, what we can see is that in this model, if we exchange two particles, if they exchange their views, then they also exchange like their spins or how they're rotating. In other words, like this is a kind of a model of indistinguishable particles, because if we swap the locations of two particles, we can't tell the difference, because now like the spin here is like the same as, you know, whatever it was, whatever the other guy was. And, you know, it's sort of philosophically interesting because these, you know, identical particles, insofar as they are distinguished, they're distinguished by their different views, as if the views were in some sense more fundamental than their, you know, supposed position. And, you know, over the years, there have been some papers where people like try to do like develop physics, starting from like these kinds of considerations that sort of the views on things are more fundamental than like, say, their positions or whatever. So yeah, so just like to summarize like this perhaps confusing thing I was trying to say before. You know, we just have this issue of like, okay, you want to start off with endpoints in 3D with like some desired spinner states. So, you know, in order to like encode this, you kind of want to have it like it, you know, you want at your initial, you've chosen like what you want the spinner states to be given some initial position. So you actually want the initial spinner state to be either, you know, the transformation associated with those positions times the spinner state, or like the adjoint of that. And then at each moment, either multiply the state by the adjoint or the whatever, so that like at the initial moment of the simulation, like you get like exactly the spinner states you wanted at those locations. And then as you drag the points around, they change based on like how they differ from that initial configuration. And, you know, what I found is that, you know, depending on whether you start with, you know, W or its adjoint, either you get like a sort of exact swap. In other words, if the particles change their locations, they like perfectly swap their spin states, which is great, very cool, but of course, you know, is missing the sign flip. In the other case, you get the sign flip, but the XYZ axes are treated differently. In other words, if you just rotate around, you know, the, you know, if you started off with the particles like arranged along the Z axis, then, you know, rotations around the X or Y axis will do the rotations and give you the sign flip and so forth. But, you know, not if they had been arranged along the X axis and you rotate around the Z. But, you know, at the end of the day, you know, maybe that's not a problem because, you know, you are kind of free to choose, you know, the coordinate system that you're working with. Like obviously the actual XYZ directions don't matter. And so, you know, you got to be paying attention to like, well, you know, what you know, relative to what is like your own axis of like, that you want to rotate them around and kind of play around with it. I don't know if that makes sense. I'm sorry, maybe that was a little confusing. It's something that becomes sort of more clear when you do this. Like, let's just look at it again. So, okay, so this one should give us the, yeah, I don't know. Huh. Interesting. As you can see, you know, this is like a area of like active research. Let's, you know, let's look at 3 guys. Okay, we got 3 guys here. And like, let's take the blue guy and we like move him over here. That's good. Now he's pointed in the purple direction. This guy's pointing in the blue direction. When this gets like this guy's phase is here. Part of the problem is that like there's like a little glitch because there's like a sort of coordinate singularity. And so this phase is like a little bit different from where it's supposed to start out. But I hope the general idea is coming through here. We have a smooth map from the space of the positions of the particles into the space of exchange rotations, such that an actual exchange in space corresponds to an exchange of the spins. And so this is like a model of indistinguishable particles in that sense. Yeah, I'm unhappy with what the phase is doing here. What's the deal with that? I guess if you just do that, yeah, I guess that's the opposite of what it was, right? You know, that's pointed away from me and like now it's pointed towards me. You know, what happens if we, oh, look at that, he's so big. What happens if we like do it from this angle? It's funny because it's like, you know, my method of like learning things is to just play around with these until I feel like I know what's happening. But it would be kind of nice if we, you know, if one has like a more analytical proof. Anyway, so it's worth mentioning that, you know, these, this kind of construction actually, you know, has been generalized to different kinds of spaces. So, you know, instead of working with endpoints in Euclidean space, like we're working with, you could do endpoints in hyperbolic space or endpoints in Minkowski space, or even spaces with like other kinds of symmetries. And people have formulated these conjectures that the, you know, whatever the polynomials or the vectors associated with the views of each particle and the other ones are going to be linearly independent. But still, obviously, this whole treatment is still basically like semi-classical. In other words, we're like still not dealing with really like position wave functions in any way. We're just sort of swapping these sort of classical positions or whatever. Although, of course, you know, we can treat the spin in a quantum way by just sort of second quantizing this construction that we've worked with. So I was just going to end on like some random thoughts about just fermions and bosons. But before I do that, yeah, like, are there any questions about this ATIA construction? You know, I can show you, like, you know, in this code here, you know, given endpoints in 3D, you know, this creates the views of each particle and the other ones by just, you know, subtracting their positions and normalizing. Okay. For each view, you know, we can, you know, given a constellation, we can form a spin state, basically. Form the matrix by, you know, having those be the columns. Take the polar decomposition, tensor with a 2x2 identity, boom, we got it. These guys generate our, you know, SU2. Well, I didn't mention the SU2 part, but this is our basis for n by n Hermitian matrices. This includes those plus the Pauli matrices that rotate the individual spinners. It's sort of like, you know, we'll split one of these two n-dimensional states into the spinners. You know, start off either, you know, we start off by taking the transformation matrix and multiplying by the state, or else it's adjoint. And then at each moment we multiply, as you know, we multiply it by either its adjoint or not, you know, of like the current view. So, you know, just for fun, you know, you can play around. The colors are so similar there. Still, similar colors. It's amazing how often you get similar colors when you just randomly generate them. All right, close enough. So, you know, boom. Here we go, 4 particles. And, you know, you can see I'm just like dragging this guy around. Spin states are evolving. And if I can arrange it that, you know, like, you know, say like, take that guy. If I can arrange it that, you see, like now this guy has a constellation that's kind of like this guy. And if I could make this constellation to be exactly that constellation, then this guy would definitely be pointed entirely in this direction, in this like light green direction. And so forth. And it's kind of interesting to think about. I mean, like, you know, I don't know if this is supposed to represent like an actual model of like 3D space or like whatever, but like, it's interesting that like, to the extent that these guys are sort of like, you know, you start off with like sort of separable spin states, and then, you know, or what I mean is like, you start off with some spinners with like norm 1 or whatever. Like as you drag this around, you see that the norms of the spinners are changing, you know, which is represented here by the radius. And in the quantum case, you know, that's going to correspond to like entanglement, you know, between the spin states. So, you know, if you started off with a bunch of separable states, then, you know, as you sort of like in this like sort of intermediate like moment when you're like dragging this guy around, you know, the spins are going to get entangled. And then like to the extent that like, oh yeah, you know, boom, like, you know, now he's got like that constellation or whatever. It's going to go back to being separable. So that's sort of interesting. Yeah, just for, yeah, let's look at this one, this other example again, just so you see. Just make it even bigger. So again, you know, we got 4 spins, 4 guys. All right, you know, take blue guy, pop him over here. And now see, you know, blue guy before had this like all the stars to the left. if blue guy's here, then green guy's has all the stars to the left. And so he's pointed where blue guy in blue guy's direction. And this guy's basically pointing the green direction. Move him over here. Now he's pointed it, he's got the same view that red guy started out with. Red guy started out with all the white stars to the right. And so now when this guy's sort of view is all the stars to the right, he's pointed in the red direction, and so on. And that works. And also, you know, it's like you get a particular state. As I say, it's like a smooth map, so that, you know, however I like drag these guys around, you know, I end up with like some spin states. And it's like, you can, as I say, you can think about it like, by choosing a starting configuration, it's like we're associating each spinner state with a certain view that's kind of like its coordinate. And if, you know, you make it so that a particular guy has a particular view, then he gets the spin associated with that view, basically, but like in a completely smooth way. So, there you go. And so it's interesting to think about, you know, what it would be, what it would take to, you know, sort of treat, you know, even the positions of everything, you know, quantum mechanically, and how that would relate to this model. Because obviously, you know, we're not dealing with the position wave functions at all. So I thought I would just end on a couple things. One is that, you know, this reminds me of stuff that I am interested in but don't understand. There's this whole field of, this whole research project, you know, known as, you know, celestial conformal field theory, where they try to develop like a holographic version of like Minkowski space, where, you know, in a holographic theory, you have stuff on a boundary and stuff on a bulk. But in these sort of flat space settings, the boundary theory turns out to be, you know, the theory on the celestial sphere. And so in a way, like, this is a sort of, maybe the, you know, one way that you can sort of generalize these ideas of like treating the views of each particle as like fundamental in some way. So check that out. You know, it's often, you know, everyone talks about the spin statistics theorem, and it's just worth spending a moment talking about, you know, statistics or whatever. You know, if you have Maxwell-Boltzmann statistics, it's like, imagine you have two distinguishable pebbles, A and B, in two boxes left and right. There's four possible states, you know, A and B both in left box, none in the right, A in left, B in right, B in left, A in right, and none in left, A and B in right. And because there's four possibilities, each has 1/4 chance of occurring. But if you had permutation symmetric identical particles, such that it was like impossible to distinguish between A and B, you only have 3 states, and each would have a third chance of occurring, and that's the Bose-Einstein statistics. You can see, you know, it's like the statistics are different of like what states you should expect to see once indistinguishability comes into play. And then finally, if you have antisymmetric identical particles, there's really just this one state thing, which this is understood to be, you know, one left, one right, but they're anti-symmetric. But, you know, it's worth remembering, you know, when we say, oh, fermions are always in the anti-symmetric state, right? It's like, it's always important to remember what happens when you second quantize, you know, position along with spin. So it's like, we have 2 electrons. It's perfectly possible for their spins to be in a permutation symmetric state, but it would just mean that their position wave functions would have to be anti-symmetric. And conversely, if their spins are in the anti-symmetric state, then the position wave functions would have to be symmetric, because the whole state, taking into account like all the shit involving these particles, has to be anti-symmetric. No, if both the spin state and the position state were anti-symmetric, then the whole state would be symmetric, and so it wouldn't work. That wouldn't be the case for fermions. So, you know, it's worth remembering that there's like this kind of interplay with the position wave function. And of course, you know, this sort of semi-classical like treatment here that we've been doing, you know, it doesn't really involve the position wave functions at all. So that's all I got. Any thoughts, questions, concerns?
Well, that's another excellent session.
Thank you, Moshe. Glad you liked it.
Actually, one problem that I had is with my microphones. I missed a good portion of it because my speakers actually did not work properly. So I guess I will have to watch the tape, the recording.
It's being recorded, yeah.
Hmm.
Yeah, sorry about that. You know, if you look at this, you know, these links, I recommend, you know, I first discovered this stuff here, these Edinburgh lectures on geometry analysis and physics by Atiyah. So he's the first, this very nice introduction to it. See, this little section here, from Euclidean three space to complex matrices. So it gives us like a very nice, clear overview of the issue, you know. You start with points in 3D, you know, you define these like the relative, the views of the one on the other, create, you know, polynomials, conjecture. Those polynomials are linearly independent. And then, you know, he talks about, you know, and he was inspired to do this by considering, you know, Berry and Robin's paper. And then, you know, he talks about how to generalize it to hyperbolic geometry, you know, Minkowski space, you know, where you're thinking about, okay, what speed are they moving at or whatever, but, you know, there's going to be Mobius transformations, etc. You know, talks about some higher level stuff. You know, maybe it even works for, you know, even more complicated stuff. You know, more abstract spaces where you can have coordinates. Anyway, yeah, I recommend looking at this and some of these other papers, and you'll see, you know, how it's sort of like a natural thing to think about, you know, after reading the Berry Robbins paper, and it's worth going through, like if you want, you know, to like go through these matrices and like kind of get a handle on like, yeah, like why is it that permuting the locations of the particles permutes the spinners, you know what I mean? Like if you kind of work out the matrices by hand, you can sort of see that it was almost inevitable. But I mean, I particularly like it because, you know, as y'all know, I love this whole constellation concept, and this is perhaps my favorite application of a lot of the stuff that we've talked about: spin, oscillator representation, constellations, polynomials, etc. So if there's nothing else, I suppose we should call it a day. Thank you all for coming.
Hey, thank you, Matt. Looking forward to next week.
Yeah, until then, talk about some cool stuff. Got something prepared. Alrighty. See ya.